have been doing on whether dark energy can affect the nonlinear structure formation of the universe. In the next part of his talk, he moved on to talking about dark matter, and then he discussed a variety of dark matter candidates. In fact, he did an incredible job of covering the full spectrum. He started from very heavy dark matter, where dark matter is a compact object, primordial black holes. He went over primordial black holes, decaying dark matter, self-interacting dark matter, warm dark matter, and fuzzy dark matter. Basically, the whole mass range of dark matter he covered, and he showed how using various astrophysical constraints you can, currently we can only constrain these models, but hopefully in the future we will be able to discover many of, either one of them or many of them. Okay. So the second mini review was given by Dr. Manisha Lohan from TIFR. She was talking about the new field of neutron astroparticle physics. Right. So we have been doing astroparticle physics with photons. IceCube started this new field about 10 years ago, and she gave an excellent overview of the various results of IceCube. So it's an astroparticle talk. So she talked about both the astrophysics results of IceCube and also the particle physics results of IceCube. Then she gave a brief discussion of what is the next generation looking like, IceCube Gen 2. All right. So she talked over she discussed various proposed designs, various neutron detection mechanisms that IceCube Gen 2 will have. IceCube Gen 2 is significantly different from IceCube, and the physics reach, both in terms of particle physics and astrophysics. And finally, excitingly, she also talked about how India can contribute to the IceCube Gen 2 construction from some detectors. All right, this will basically be the best neutron telescope for the next foreseeable future. So that's very exciting. The next talk, mini review, was given by Dr. Divya Sachdeva, where she talked about dark matter indirect detection. All right, so this is one way to detect particle dark matter, and she basically talked about dark matter indirect detection using gamma rays. So she gave a brief overview of how this detection mechanism works. She talked about the current limits that we can get from dark matter indirect detection, the medium term and the long term prospects. And then she also pointed out, as part of her talk, that dark matter indirect detection inherently combines astrophysics and particle physics. In fact, she pointed out that given some of the astrophysical uncertainties that we have currently, we can get extremely strong limits on dark matter on dark matter properties, all right, which also implies she used the Hess and Veritas data. So these are gamma ray telescopes which can look at the galactic center. Using their data, she derived the most stringent limit on dark matter annihilation cross section, and then she also mentioned how upcoming telescopes like the Cherenkov telescope at ACTA can do a great job in either discovering dark matter in the given mass region or ruling it out. Good. So the next was a review given by Professor Soma Sannal on topological defects in the universe. Here she first started by talking about the motivation of why these topological defects must exist, right? And she gave a nice overview that saying that if symmetry breaking phase transition exists, these things must exist, all right? The point is at what scale. Then she gave a overview of various kinds of topological defects that we have, string wakes, cosmic strings, superconducting strings, abelian Higgs strings, and how to detect them in various experiments, right? Either cosmological experiments or astrophysical experiments. For example, she was talking about fast radio bursts, gamma ray bursts, where we will have lots of data coming up, right? Where we can actually hopefully detect these topological defects of the universe, and that will be revolutionary in cosmology. Okay, so these were the 4 reviews. We had 40 parallel session talks covering a wide range of topics. I will try to go over them quickly. So this was a highlight of the parallel session on Monday. So it started by a talk on QCD physics. Basically, how does QCD look inside neutron stars? That's an important problem, and astroparticle physics observations can do it, given by Harish Chandra Das. Then there was an effect of milli-charged dark matter in black hole shadows, how we can use these new observations of black hole shadows to possibly discover milli-charged dark matter. This is given by Lalit Singh Bhandari. Ranbir Sharma talked about how to do cosmological data analysis and figure out some of the parameters that the data can probably indicate, right? Using some new data analysis techniques. That was super interesting. I mean, I gave some of the figures where the slides were available on Indigo. There was the overview of GRAPES-3 experiment by Pranab Nayak and Medha Chakraborty, where they talked about the muon and cosmic ray events. More precisely, there was this cosmic ray anisotropy map from GRAPES-3, which is again a very exciting discovery. Professor Soma Sannal talked about cosmic string wakes. This was a more technical talk that she gave, which is again very interesting. Pethuraj Shankar Narayan talked about how mini ICAL has detected muons, and he talked about some of these the statistics of them. And then finally on Monday, Prantik Sharma gave us a model of what can produce high energy gamma rays and neutrinos, and whether it can be detected by using various telescopes. Okay, so Tuesday, Mohali Chaudhary talked about studying some of the CDMS2 backgrounds. This is a super interesting study because this is something that CDMS can use for super CDMS experiment. Right? So, this was actually very interesting. Then there were talks by Pritam Das and Anirban Vishwas, where they talked about how dark matter can actually be connected with neutrinos. All of them are weakly interacting, and how you can probe them, right, by using cosmology. Deepti Ranjan Patnaik talked about the angular resolution and pointing of the GRAPES-3 telescope. It's very useful when GRAPES-3 starts detecting astrophysical point sources of gamma rays. Professor Vishwanath Laik talked about phase transition inside pulsar core using pulsar profile modulation, again something which astroparticle physics can do to help us learn about QCD. There is an interplay between QCD and astroparticle physics here. Bikram Pradhan talked about hyperons inside neutron stars, again on the same topic. Kaushik Loho and Abhishek Roy talked about dark matter phenomenology and model building. These are one of the plots from Abhishek's reading. And then finally, Dr. Richa Arya talked about how you can produce primordial black hole dark matter from warm inflation. Right? This is one of the models of inflation. Yes. So Wednesday started with Prashant Shukla talking about cosmogenic particles via simulation study. This is very useful to understand what we are detecting in experiments. Does it match with theory or not? If it doesn't match, it may be some new physics or maybe some misunderstanding of the standard model. Shashank Shekhar Pandey talked about how the inhomogeneities in the universe can affect the gravitational wave propagation, right? And this is one of the plot from his talk. Deep Ghosh talked about how to produce asymmetric dark matter, right? Asymmetric dark matter where there is dark matter but there is no anti-dark matter. How to produce that? So he talked about a very nice model, the most minimal model that you can do to produce it. Lakhvinder Singh used experimental data to produce some of the leading limits on axion-like particles. Actually, some regions there were the leading limits. Anirban Chatterjee, Dr. Anirban Chatterjee talked about late-time cosmology and dynamical stability approach, basically trying to see how what you can do for dark energy. Again, something very interesting to look forward to. Chitrak Sarkar talked about primordial black hole formation in some models of inflation. Debojit Ghosh used all the neutron stars in the galaxy to detect dark matter, and they showed us the best limits on dark matter in some parameter space dark matter using this technique. And finally, Dibyendu Nanda talked about how to probe high scale non-thermal leptogenesis using cosmic microwave background radiation. Thursday, so this is the last day we had the talks. Initially started with various talks by GRAPES-3 by Zubairi and Varsi, where they were talking about cosmic ray diurnal variation and the GN4 simulation package for GRAPES-3. Abhijit Kumar Saha showed how the great power of cosmological observations that we have to probe various dark matter models at the MEV scale, mega electron volt scale. Priyank Parashari talked about how we can use current Lyman alpha forest measurements to rule out various parts of parameter space of primordial black holes. Dr. Tanmay Poddar talked about how light vector gauge bosons, if they exist, they can affect the GRB emission, right? And what are the constraints on the plot from his thing. Bhanu Pant talked about the leading limits that GRAPES-3 has found in 10 to 300 TeV isotopic diffuse gamma ray background, right? And for some regions of the parameter space, they are basically the leading limits in the world. Arvind Kumar Mishra gave a brief overview of primordial black hole formation, again from some different inflationary backgrounds and its gravitational signature. Ankit Kumar, this talk was actually held earlier, but it was listed on Thursday, so I just listed it for simplicity. Talked about how dark matter can be inside neutron star by some mechanism, and what are the effects of it. How do neutron star properties change if there is dark matter inside neutron stars. And finally, Mohammad Ramiz reminded us that although all of these talks were assuming the standard cosmological model, and sometimes we must step back and analyze the data and see if the assumptions on which the standard cosmological model exists, are they real or not. I mean, can we confirm it? So he gave a very nice talk on how to check the assumptions of the standard cosmological model, and he mentioned that all of the data, this is a very controversial talk, but he also mentioned that all of the data and all of his code is publicly available. So any of us can download and check this, right, and this will be an extremely important thing. Okay, so then there are poster sessions. So here obviously I cannot go through all the posters, all of them are great. I'll just tell you some of all the topics. There were lots of posters on cosmology. These are the people who worked on it. Note that here there is some overlap, all right. So I mean, dark matter is also cosmology, but I've put it separately just for simplicity. There were lots of posters on quantum chromodynamics and nuclear physics, especially how astrophysics observations can let us learn more about it. All of these people gave some great posters. There were many talks on dark matter, how you can detect dark matter, how you can produce dark matter, and all other things. Again, there were excellent posters by all of them. Cosmic rays, how measurements of cosmic rays can help us understand various things about standard model physics was given by these people. Astrophysics, there were astrophysics related talks. What can we learn from astrophysics and how can it help us improve our understanding of the universe? Again, there were some excellent talks, excellent posters by all of these people. And finally, there were some talks on some posters on gravitational waves. I mean, especially in various cosmological contexts and how do they get, I mean, they arise and what are the effects that we can observe. Again, some excellent posters. Anyway, so first of all, I would like to thank all the participants of all the working groups, everybody that's present. Wish you all the best and looking forward to even more brilliant physics from all of you. Thank you.
So thank you for summarizing. So if there is any quick question or something, for summary, I don't think there should be. Okay.
Thanks.
So if not, thanks again the speaker. So next is the working group 2, beyond the standard model. So let's see what's beyond for us. So 3 minutes, I will tell you about 3.
Keep my phone here. So that's okay. Hello. Yeah. Okay. So Ranjan has already set a very difficult task for me by going through too many details of what was covered. So anyway, so I'll go through quickly. So as you can see, the first slide also doesn't have a name. I'm Santosh Rai from Harishchandra Research Institute. So none of the slides will have names of the people who have given the talk. So I'll just summarize what has been covered in working group 2. So as you can see, BSM covers a host of things. I think each of the subgroups that have been kind of discussing issues on in particle physics or cosmology will have something to do with BSM. So anyway, so let me just go through quickly. So we had 2 mini review talks and 23 seminars of 15 minutes each, and these were the broad topics that were covered. So we had some 88 or 90 odd abstract submissions, so you can count the rest of them went to posters, okay, with a few rejected. So the broad classification was that we had talks where BSM searches were kind of discussed, which were done at CMS and ATLAS experiments. Then BSM models were presented, which looked at dark matter and neutrino mass. Then BSM phenomenology at LHC and future experiments were discussed. And of course, there were several talks on issues of baryogenesis, anomalies in flavor, and fermion masses and other things. Okay. So let me go to the first one. So this was discussed in the context of the dark matter searches. So it was a very simplified model looked at in the mono X signal, and this study was done at CMS. So the work presented actually dealt with what kind of a mediator mass and the dark matter mass could be probed at CMS experiment in the mono X channel. So the mono X in this case was a photon, which was basically radiated up from the initial state. Okay. So this is the limit that they have of around 1 TeV. Mediator mass has been excluded for about 1 GeV dark matter mass. So this was a 2016 result, which was published in 2019. Okay. All right. So the next was discussing the charged Higgs. Well, the model of concern was the 2 Higgs doublet model. So this is the most basic 2 Higgs doublet model, and then of course the observation of the charged Higgs in the decay channels of the top quark. Okay, so the charged Higgs was lighter than the top, and so this was the limit which was derived through this analysis by CMS, and this work was presented in one of the parallel talks. Okay, so the next talk again was CMS analysis on looking for resonances. So this is very similar to looking for the Higgs in the Z gamma mode, which is the rare decay channel of the Higgs, and so any other new resonances which can show up in this Z gamma mode was looked at the CMS in this particular channel where the Z decays to dileptons. And so this whole thing can be reconstructed. So the mass limits were discussed in this talk based on this sample of data. Okay. So again, this work is in progress. So only the basic experimental analysis setup was discussed, where the control regions were discussed and so on. This was more of a exotic fermion search, so vector-like quarks. So this is a T prime, so the exotic partner of top quark in a simplified model again, where the top quark can decay to a top and Higgs. So the search channel basically discusses fat jets, so in the sense that this T prime is heavy and then you have a boosted top and a Higgs, and based on this fat jet structure, again control regions were discussed, and again this is also work in progress at CMS, so only the basic standard model background was discussed of how the analysis has been set up. Okay, so I have time. Okay, good. Okay, so the next talk, of course, again is an experimental talk. So this was in the vector boson fusion channel, where you have the chargino-neutralino production, and then you have basically large rapidity gap between the forward jets and no color activity, and so it was looked into leptonic channels. So again, this was basically the results that the signal region predictions gave for different masses of the charginos and neutralinos. Okay, so this was in a more exotic SUSY scenario of the gauge mediated supersymmetry breaking, where the neutralinos actually decay to a light gravitino. So it's a very light gravitino, which is basically present. So you have a neutralino decaying to a very light gravitino, so you get very high PT photons from these decays of the neutralinos, and so this search was discussed in this experimental work. Okay. So this is the typical signature, that when you have one photon and lepton and large missing ET. Okay, so now, so those were the experimental talks which were basically discussed. So most of them were CMS analysis. Again, now we move on to the phenomenology aspects, and search is proposed for BSM at LHC and electron-positron. Okay. Yeah. So okay, so this was basically the anomalous coupling, the HVV anomalous coupling, where the azimuthal correlation was looked at, and one basically predicted what could be the sensitivity at an electron-proton collider like the electron ion. I think this analysis was more of LHEC, Large Hadron Electron, yeah, LHEC. Okay, so then the search for, again, an inert Higgs doublet model, so where the lightest Higgs, neutral Higgs in this case, of course, is the dark matter candidate, and so one looked at this particular channels where you have large missing ET because of the dark matter, and again a boosted topology was looked at for the search for charged Higgses, or the inert Higgs doublet model in that sense. Then of course we had a talk on anomalous magnetic moment, which is of interest now because of the G minus 2 of muon, and the solution was provided in a MSSM scenario where non-standard terms were added. So these kind of terms, soft terms, were added in the Lagrangian, and then they discussed what the loop contributions would give in presence of these terms, and the scan was done on the parameters involved here, and they got a region of parameter space where this could be explained. Okay, so then the neutrino masses and mixing angles in context of bilinear R parity violation, where you have the neutrinos mixing with the neutralinos. So you have a larger 7×7 matrix over here, and also if you had bilinear R parity, then you also can generate the neutrinos will mix with the Higgses, and because the neutrinos now don't have this, so the lepton number is violated, so you can mix the neutrinos with the Higgs and you get contributions in the loop. So you have 3 level contributions and 1 loop. So they looked at the parameter space, which kind of explain the neutrino masses and mixing angles. Okay, so then more exotic models in the sense that you have models for neutrino masses, which is the type 2 seesaw. You have a triplet scalar added to the standard model, so you have double charge Higgses, so the production of double charge Higgses. So this work actually looked at light double charge Higgses, and in the fat jet scenario where the light double charge Higgs decays to W's, and so the W's will basically give you fat jets. Okay, so this is a boosted topology, and they kind of found the sensitivity at LHC. Okay. Another work which dealt on the left-right symmetric model, which also has double charge Higgses, looked at a scenario where a dark fermion is added, a doublet, vector-like doublets which act as dark matter, and so you, instead of getting resonances in the double charge Higgs, now you kind of get a large missing ET. So it's a different kind of a signal. So now let me just quickly go through last few slides. So this is again a left-right symmetric model, but it's embedded in a E6 gut, and so you kind of get dark matter, fermionic dark matter in this model, and again adding extra terms, higher dimension of terms in the Lagrangian, you tend to get new decay modes for these fermionic states, which are in the theory, and you get new signals for them. Okay, and they also help in the dark matter analysis. Okay, so I won't go into the details of this. Of course, this is NMSSM plus right-handed, so they looked at this dynamics of these fields, how they affected the electric phase transitions, and then again this work actually dealt with electric phase transition and gravitational wave signatures in the inner doublet model with extra scalars. Okay, so I think this was a work on clockwork mechanism where the fermion masses were kind of derived out of the clockwork mechanism. So again, not much details over here. Then this work actually discussed the vector-like top quark partner and what were the signals for these. Again, where one extra new scalar is added, so you have a non-conventional decay of the vector-like top quark. Okay. All right. So again, this also looked at a similar kind of a scenario where you have now a top quark decaying to a top and a photon, which is again a dark photon, you can say. It's a dark matter candidate, so you get sensitivities where a vector-like top decays to a dark matter and a top quark. All right, I think it's yeah, and so this is the last one. So this I think Rahul already talked about in his plenary talk about gauging the B, L or the B plus L to get a higher dimensional operator where the symmetry is Z3. Once the U1 next breaks, so you get higher dimensional operators for the proton decay, and you can get lighter scales of this new physics, which can be of the TeV scale, which can be probed at the using the proton decay. Okay. So yeah, those were the talks in the parallel session for working group 2. Thanks.
Thank you. So any question or comment? So no, thanks again the speaker. So next is like for the working group 3 formal theory. So Dr. Anush Joseph. So somehow the summary has to be done by the LOC instead of the conveners. 10 minutes.
So this is the the summary of working group 3 formal theory sessions, more than one. So we had 2 days with 2 sessions, sessions 2 and 3. So on day 1, session 2, there was a mini review and there were 4 talks. And on day 2, session 3, we had 5 talks. 1 person did not show up, so we had only 5 talks. So mini review was by Loganayagam from ICTS Bangalore. So he talked about OpenQFT and holography. So here is what I copied from his talk. So in the talk, one of the 2 main results, the 2 main results were first derivation of 2 derivative hydrodynamics action from gravity, then an open effective theory action for fluctuating hydrodynamics from Einstein-Hilbert action. So they have constructed a map connecting these 2, fluctuating fluid configuration and slow Hawking gravitational wave configuration. So then there is a question, are there similar long-lived slow fluctuating modes governing the evolution of our universe? So then we had 4 talks, mini talks. First talk was by Supratim from Granada. RGs and positivity bounds on the standard model effective field theory, dimension 8 operators. So they looked at dimension 8, insertion of dimension 8 operators in the Lagrangian and the effects. So here the summary is renormalization of bosonic standard model effective field theory operators by dimension 8 tree level generated operators are mainly discussed. Okay, so talk 2 was by Sumit Das from SANP, Kolkata. So here in this talk he talked about black hole normal modes and spectral form factor. Yeah, so here they considered a model which they call scalar in stretched horizon scenario, and they compared that with the SYK model. So they are getting similar results. So here there is a slope one which is interesting. Yeah, so they are also getting the for the spectral form factor, the dip, ramp and plateau. Yeah. Okay, so next talk was by Sandeep Maiti from SINP. So here he talked about massive fermions without symmetry breaking in 3 dimensions. So they studied the 3-dimensional Gross-Neveu model with 2 flavors of fermions, and they discussed an alternative mechanism for mass generation via fermions. So they observed a second order phase transition. So these were all numerical calculations. So then talk 4 was by Vamika Longia from IISER MOHALI. So she talked about investigating the 2-dimensional, oops, sorry, there is a change in title, but topic is, overall the theme is the same. So tensor renormalization group analysis of 2-dimensional generalized O2 model. So the results are, so they are observing, I am also a co-author of the work. So 2 phase transitions depending on a parameter delta. Then there is also a BKT phase transition in the model. So again, these are numerical simulations based on tensor networks. Okay, coming to day 2, session 3. So there was, the first talk was by Astha Kakkar from University of Delhi. So the talk was about analysis of phases of scalar field theories in thermal ADS spaces. So there is a long list of summary. So hopefully we will upload this to the Indigo page. So they gave a derivation of scalar one loop partition function using this particular operator in Euclidean ADS. So they studied the phases of scalar theories on thermal ADS D+1. So they observed the symmetry, two phases, symmetry preserving and symmetry breaking phases. Okay, second talk was by Chandrasekhar from IIT Bhubaneswar. So Chandrasekhar talked about holographic local quench, complexity, and chaos. So here the result is the momentum of infalling particles in this particular black holes shows a suppression in chaotic behavior as the charge reaches a critical value. So they studied an operator, a particular operator, and it is also expected to show a similar behavior. So as you can see, there is a wide variety of topics in the formal theory sessions. So next talk was by Kajal Singh from HRI. So she talked about statistical aspects of string landscape. So again, several results. So they studied the distributions of the gravitino mass and axion physics in KKLT and LVS models. So here LVS stands for large volume scenario. So again, several results. Yeah, and some remarks. Then the fourth talk was by Rajiv Gawai from IISER Bhopal. So Rajiv asked the question, is the lattice fermionic cosmic effect universal? So the result, the summary is, here's the definition of Casimir effect. So it should be investigated in theories with non-trivial vacuum, such as QCD. So earlier studies of lattice fermion, Casimir effects showed a violation of universality. So so depending on the lattice discretization, we can get different results. But here the authors employed the MIT bag boundary conditions and showed that all types of fermions lead to the same continuum result in the lattice spacing going to zero limit as expected from universality. So this is what we expect. So there is no surprise there, I think. I mean, this is what is expected. Okay, then fifth talk by Sudeepan Datta from IISc Bangalore. So they are looking at automated evaluation of Feynman integrals using GKC hypergeometric systems. So if you look at, so there is a Mathematica package. If you try to evaluate the Feynman diagrams using, these packages, and if you look at the loop structure, and they can contain very rich mathematical structures. So we can make use of those structures to compute these integrals easily. So that is what they were doing. So they introduced a new algorithm, and it was proposed in this work, summarizing all this. So I guess that's it. Thanks.
So next we have the working group 4. So for the detector development. So Professor Behra will going to summarize.
Hello. Good afternoon. So I will summarize for the session future experiments and the detector development. There are so many groups working in India. It will be very difficult to summarize everything in 10 minutes, but we will have the proceedings and everybody will be accessing, and if you are interested, you can read it. So we have three conveners, Deepak, Samuel, myself, and Subhasis. So here I am going to present. So this is the session. So we had Monday, Tuesday, Wednesday, Thursday. There are 5 sessions. We had 5 parallel sessions. There are about 28 talks, each 15 minutes. Then there were 2 mini review talks, were 30 minutes each. We had 52 posters, and during the review, Professor Naimuddin and Prasant Sukla helped us to review the abstracts. So we would like to thank them. I have picked a few of the interesting results, what I thought, and I'll just flash it. First thing is silicon detector development in India. So this is the mini review talk given by Kamesh. So he reported what is the difficulty in building this high-tech detector, and this being nicely summarized, the difficulty they face during the development for Bell 2 experiment. So for this detector you have to, what all this table tells you, that mechanical precision is very important. You cannot make the compromise on the precision. So what they found, that this is called design issue. Let's say if you see there is a wire here slightly bending here, they thought it's okay. When they make the production, they found that this portion is not staying as it is. At that point you cannot redesign but to find a solution. So if you have this issue, you have to throw the module. It's very expensive. So what they have done actually to avoid this issue, they put the reinforcement in Mylar sheet to keep it stay there. If it is not, you can put the 2 Mylar sheet. This is a nice out of box solution which you never thought, but on the way you can use this, very nicely done, and this detector is nicely running for Bell 2 experiment now. Next one is given by Irfan, who talk about the Egical, which is a future detector for CMS upgrade, and this is one of the hot topic because now silicon is going to be used for the calorimetry. So what is gave the idea that you can have this silicon with a sandwich between the different material. You can use as the granularity, means position resolution you can improve, and you can do the precise energy measurement. And this is being done also from Indian group. Next was given by Mohesh from Delhi University. It's very interesting that in India, so many groups are working on gem detector, and we are using gem for many different experiments. Now it is time to look beyond the particle physics, and it is so that how you can use gem detector for imaging. And he has shown nicely in the lab, he has taken some of the material here and used the gem detector with the radiation source, and you can see nicely the image, and you can improve the quality. This is a fast way to look the spin off from the particle physics detector technology to societal application. Next is a interesting topic given by Mandar, that you know we have a very ambitious project, experiment, though it is delayed, but there is still effort to do this experiment, and he showed that whether we can use the muon veto to do the neutrino experiment. This is just a proof of principle they are going to try. They use plastic scintillator detector cover to the IISER detector, so that atmospheric muon can be vetoed by the scintillator detector, and they show that the rejection you can get 99.99%. Okay. Though they are trying to build it in Madurai, and the result from this will show whether we can do this or not with a shallow depth. We can put the detector not in the underground, but we can put the detector maybe 100 meters down the ground. This is a nice initiative. Another aspect which given by Bridge, this is very important for all the experiment that trigger. So if you are working in any collider experiment, trigger is most important, and trigger at makes your life difficult because we are going to have high luminosity LSE. So what he showed actually, now there is a proposal, already it is being implemented in LSEB experiment. You can remove the hardware trigger. If you remove, you can put this all in software trigger and you can accommodate more rate. So this is the way to go, how to go for high luminosity LSE. And now CMS and Atlas are trying to implement, though it is not the same detector, but this shows that there is a room we can learn from here and apply for the CMS and Atlas. So using this detector, LSEB shows very nice distribution of D0 and JEPSI. There is no compromise on the performance of the physics. So this is a very nice proof of principle demonstrated, and CMS is trying to use as much as possible to improve the timing. So once you have time, then you can take the more bandwidth. So there is a nice talk by Sandeep about the Hagar experiment. They are going to renovate, I would say. They are trying to redo the back-end electronics and front-end electronics, and he had shown that how the temperature dependency can show you for the performance of the SIPM, and with the correction you can make it flat. And there is a significant progress has been made for the electronics, and they are happy to see that this maybe they can run this experiment in the near future. Big thanks to the oral and poster presenters. So I might have missed your talk, but we are supposed to finish in 8 minutes. Thanks to NOC, LOC members and volunteers for the smooth operation. Thank you.
Thanks, Professor Prafulla. So any comments? If not, so thanks again. So next we have working group 5, heavy ions and QCD. So Dr. Natasha Sharma is going to summarize it.
Good afternoon, everyone. I am going to present the summary of the working group 5, which is the heavy ion and QCD. First of all, I would like to thank the local organizer for having me on this platform and making me as a convener and contribute in this session. So here is a list of the conveners. So there is Professor Bedanga Das Mohanty, Partha Baduri, myself, and Meduri, and Siddharth Kumar Prasad. So Siddharth Kumar Prasad, he could not come because of some personal reasons. Rest we all were here, and we attended all the sessions, and I would like to thank all the speakers. I could see their hard work, especially the younger colleagues, and I could see that how much work they are doing, and it was very nice having them here. Okay. So we had 4 mini review talk. First one was from Tobias Stoll, another from Ekta Chobe, Raghunath Sahu, and Roli Isha. So in total there were 8 sessions, around 40 parallel talks, and out of these 40 there were 20 dedicated to theory and phenomenology and 20 were the experimental talks. So now I am going to present only very few selective results. Please pardon me, and to all others whose result I am not presenting here. So first is the theory talk about the initial gluon profile, and I am an experimentalist, so please bear with me. These are theory slides if I don't say something properly. So, the speaker, he used some model in which he claimed that there are hot spots inside the nucleons, and within these hot spots there are more hot spots. So, he used various models and various parameters, and he then tried to describe the initial distribution of energy density. So, these are the results which he compared with the different the models, and he claimed that their model indicate that the incoherent cross section will saturate at small x, while the coherent cross section will grow. More details you can find in this publication. Then there is another talk by Rolisha. So, she this is one of the plot from her talk, and here she tries to measure experimentally the net proton C6 by C2 as a function of the collision energy. So, and these points are the experimental data point from the star experiment, and these various lines are the model predictions. So, C6 by C4 for 0 to 40% centrality is increasing negatively with decreasing energy, except at 3 GeV where it is positive. So, this is what the experimental data shows us. The negative sign of C6 by C2 is consistent with the QCD calculation for mu b less than 100 MeV. So, these are these that indicate a crossover quark-gluon transition. Peripheral 50 to 60 data and calculation from URQMD model, which does not include any QCD transition, they are either positive or consistent with 0. So, data shows that there is something interesting happening between this energy range. So, the search for the critical point is still ongoing. Then there was a dedicated section on resonance production, and there were talks like resonance production and hadronic phase in heavy ion collision with Alice at LHC by Sandeep Doody, and there was talk on similar topic by Sonali Pradhan, and there is another talk by on production of K0 star in gold-gold collision at 19.6 GeV using the star BS2 data by Ashwini Sahu. So, the plot here shows the particle ratio, which is the K0 star by K, phi by K as a function of the dn charge by data. The points here are the experimental data, and lines here are the model prediction. So, it is seen that K star 0 by K suppression means that rescattering of resonance particle in hadronic medium, and phi by K we see that no effect is seen, it remained constant. So, no effect of the hadronic medium on this ratio. Similarly, RAA is the nuclear modification factor. So, this is studied as a function of the PT. So, in this RAA is the for the lead-lead collision, and RP-lead is for the P-lead collision. So, high PT, which is greater than 8 GeV. So, RAA is less than 1, which shows suppression. That means there is presence of the medium, and light flavor hadrons, these are the various light flavor hadrons, they are consistent with each other at PT greater than 8. So, that means in this region, that means no flavor UDS dependence is seen. Whereas, if you look at RP lead, so for the high PT, that means PT greater than 6 GeV, so that means in this area. So, RP lead is equal to 1, that means no suppression is seen, that means there is absence of the nuclear effect, and these are for the various light flavor hadrons, these results. So, light flavor hadrons are consistent with each other at PT greater than 6, that means no flavor UDS dependence is seen. Okay. There is also a talk by Arushi Dhimija on production of identified charge hadron in gold-gold collision at 54.4 GeV using the STAR experiment. So, she presented the transverse momentum distribution of the pion, kaon, proton and their antiparticles, and she has used the blast wave fit to describe the data, experimental data. And from here she extracted the kinetic freeze out temperature as a function of the as a radial flow velocity, and she sees the anti-correlation. The point here shows the experimental data. These are experimental data at various energy. So, anti-correlation is seen. Then from here she extracted the Bjorken energy density. It is the initial energy density in the central rapidity region after the two nuclei pass each other. So, this is the Bjorken energy density as a function of the n part for various energies. Then she have also shown the Bjorken energy density times the formation time tau, and it is seen that it increased with the increasing centrality and energy. So, this is then another interesting results. So, there was also one talk by Protay Das, and he presented talk on the search of the CMW in the Alice experiment. So, he used the charge dependent elliptic flow, and then there is a CMW observable, which is the R normalized delta V2, and these are the various expressions he has used. So, these are the experimental data of the CMW observable as a function of the centrality. So, it looks almost constant. So, it is believed that if this observable is greater than 0 and this delta V2 is greater than 0, and for R for delta V2 is greater than R delta V3. So, this plot here is R delta Vn for V2 and V3, and these looks consistent. So, from here it is concluded that CMW signal is consistent with 0. So, it is not seen yet. So, then there is a talk by Jyoti Babbar. She talked about the discrimination of quarks and gluon jet in 13 TeV in the CMS experiment. So, she talked about 3 discriminator using the under construction by CMS. So, one is the quark gluon likelihood, another is a deep jet discriminator, another is a particle net discriminator. These 2 discriminators are based on the neural network with many input variables. And the top one, quark gluon likelihood, is constructed for quarks and gluons discriminator. It varies in the range 0 to 1. So, if there is a peak at 0 for gluons and there is a peak at 1 for quark, the plot here shows the quark gluon likelihood discriminator, and this is normalized to unity. So, the red one is peaking at 0, which is the gluon jet, and the blue peaking at 1 are the quark jet. So, the plot here shows the misidentified ratio as a function of the UDS jet efficiency. The blue line is for the quark gluon likelihood, and the red is for the deep jet discriminator method. So, from here it is concluded that the deep jet discriminator is able to explain the data, have less misidentified rate. So, it is better, shows better performance than the quark gluon likelihood. Then there was a dedicated session on the elliptic flow. So, here I show few results, and one is from the Rishabh Sharma. He talked about the elliptic flow of the light nucleon in gold-gold collision at various star energies, and the Priyanshi Sinha, she talked about probing the nuclear structure using elliptic flow of strange and multi-strange hadron in the isobar collisions. So, Rishabh, he showed the V2 by the number of nucleon plotted as PT by A for various particles. Okay. And it is seen that the V2 of light nuclei, it obeys the mass ordering, mass number scaling within 20 to 30%. And Priyanshi, for the isobar, she has used the ruthenium-ruthenium and zirconium-zirconium collision. And she, from her experimental data, she claimed that ratio of V2 between ruthenium-ruthenium and zirconium-zirconium collision at 200 GeV for K0 short, lambda and psi show a deviation from unity by 2% at central and mid-central collisions. So, it may indicate that nuclear shape and structure is different in the two isobars. So, then there is also full dedicated session on the fluctuations. So, this is one of the slide from the Tulika Tripathi. She presented event by event fluctuation of mean PT in lead-lead and zirconium-zirconium and xenon-xenon collision. So, this is the experimental data, and the green band here is the Hijing model, and the dotted line here is the Hijing power law fit. So, this is the expression for the power law fit, and it corresponds to the simple superposition scenario. And it is seen that the experimental data is not explained by this Hijing. So, clear deviation from the simple superposition scenario is seen. So, as a function of the multiplicity, and the right plot is a PT fluctuation over average PT, and this is for the xenon-xenon. Same conclusion was drawn from here. And then this is a theory part which I am not able to understand properly, but I know is interesting. So, there was a talk from Amlan Chakravarti. So, he presented 3 loop, 4 parton scattering. This is it's a last. Okay. So, he used the full analytic computation of all the parton channel, quark and gluon, quark anti-quark going to gluon, and then gluon, and then this was the first analytic computation of all 3 loop 4 parton amplitude, and he verified the Wilson line prediction, soft anomalous dimension structure of 3 loop multi-parton QCD amplitude, and he claimed factorization behavior of 4 parton scattering at high energy, and extraction of the 3 loop gluon rake trajectory in full QCD. So, these are the list of the various parallel talks, and that's all I would like to thank.
So, thanks Natasha. So, quick comment if someone wants to. No, thanks again Natasha. So, next we have like a working group for the Higgs summary by Dr. Suman.
So, thank you. So, I am not a Higgs convener. I was just asked by the conveners to talk about the summary in the Higgs session. So, I am trying my best. Let us see. So, in Higgs, we had a summary talk, review talk by Professor Kajri Majumdar, who talked about the measurements of Higgs boson. So, which is summarized in the Nature paper, which is kind of talks about all the full 1-2 measurements we have in the Higgs sector from CMS. So, here we have the signal strength for different production mechanisms, and here we have the signal strengths for different decay bunching ratios. And there are some modes for which we do not have sensitivity yet. So, we are trying our best in these channels, but for others, so we are still, so right now we are consistent with the standard model prediction, and we have also this coupling versus mass plot as function of. So, of course, in standard model this predicts a linear relation, and we see that our data are on top of this line. So, this is consistent with standard model. So, Then Kajuvi also highlighted the two recent Higgs measurements. One is Higgs 2 CC valve, where we added this graph neural network based jet tagging to enhance the sensitivity. And there we actually found more than 7 sigma signal for the Z2CC, and this was the first time in a hadron collider for more than 5 sigma signal for Z2CC. And now for the H2CC, we have the best limits from LHC, and the boosted category, which is the March jet, it helps a lot, and thanks to this graph neural network based jet tagging. In CMS, we have also measured the Higgs decay width, and is this nice idea that your on-shell Higgs production depends on the Higgs width, where the off-shell production does not. So you can take a ratio of on-shell and off-shell productions, which gives you the decay width. And here you see the decay width for different final states. So use the Higgs 2 ZZ and then Z. So one Z can decay to leptons and the other to neutrinos or to leptons. So use different final states and combine the results. At the end, we have the evidence of off-shell production. So the sigma is not equal to 0 for more than 3 sigma, and the measured Higgs decay width is roughly 3.2 MeV. So here I should mention that we assume that the Higgs coupling are same in the on-shell and off-shell regions, but in my talk, I showed that you can also change the coupling in different mass regions, and then that you can use to construct the anomalous couplings. Okay, then we had the DAE-Higgs talks from Shomo and Shondip. So in the DAE-Higgs productions, you can have from gluon-gluon initial state, so gluon-gluon fusion, and also in VBF, vector boson fusion. So in the Higgs, you have the access to this trilinear Higgs coupling, and then also the VBF mode gives access to this particular 2 Higgs to vector boson coupling. And there are, depending on the Higgs, these 2 Higgs decays, we have different final states. Of course, if one Higgs decays to a pair of B quarks that has the largest bunching ratio, so we use that extensively. Shomo talked about the results from these 3 final states, and Shondip talked about the ones which gives rise to multi-lepton final states. And at the end, using the full 1-2 data, we combine the results from different final states, and in general, the maximum sensitivity we get from BB gamma gamma, BB tau tau, and 4B. So the 4B is the maximum in the expected case. So Shomo talked about this likelihood scan as a function of this triple Higgs coupling, and then from there we have the current bounds, and also he showed the scans as a function of this double Higgs, this 2 Higgs to vector boson coupling. And the interesting thing is that from this measurement we exclude this coupling 0 hypothesis by 6.6 sigma. Okay, Shondip also talked about the case where we interpret the search, this Higgs searches as a resonance search. So you can have an X mediator decaying to 2 Higgses. So and the search was performed for a range of these resonance masses, and also it is shown how does the different final states give rise to different constraints. In the next talk, okay, now this talk from Aditya. So he talks about the fact that you can use this Higgs to epsilon gamma decay, which is tiny in standard model thanks to this destructive interference between this direct and indirect decay mechanisms. So it's very tiny, and you can use all the current results to probe the sign of this Higgs to B coupling basically. So if you add the direct search for Higgs to epsilon gamma and Higgs to and DAE-Higgs searches, there are only regions which are around coupling just standard model prediction, and thus with a wrong sign, a negative sign, which are still allowed. And if the coupling is negative, then the predicted bunching ratio is almost twice than what we have in standard model. So this is very interesting. They showed that in the indirect case, you can have different new particles in the Higgs to gamma gamma loop, which can change the Higgs to gamma gamma bunching ratio. Then we have talked from Chinmoy on the resummation for the histogram process. So he first showed how does the different perturbative orders, the correction from different perturbative orders look as function of the ZH invariant mass. So this PP2 Z and Higgs. So when you have at next leading order, you have correction from 30% and then goes to 20%. When you go to next leading order, there is a sharp increase. So, and then when you go one order above, this is close to the previous one. And then he showed how does the resummation of soft gluons, that correction look like for different orders. And then finally, they computed the scale systematics from the renumeration and factorization scale. Now, and they show that at N3LO plus N3LL is of the order of 0.1%. And they have also results from the from P to WH. Here I show only the results for P to ZH. Okay. Then we have talked from Ramkrishna on TTH, top Higgs coupling. So he first showed the TTH Higgs to BB final state. So there the CMS uses this artificial neural network discriminant to look for this TTH Higgs to BB signal, and you can see a tiny signal at the right end. And with 2 years of data, without full 1 to yet, we have an observed significance of 3.7 sigma. And in Higgs to gamma gamma, we use the full 1 to data, and we see the significance of 6.6 sigma. So it's more than 5 sigma. And also in TTH Higgs to multi-lepton, we use a BDT to extract the TTH signal, and DNN to extract the top Higgs signal. And here also for TTH, we have observed significance of almost 5 sigma. So just only using this particular final states, not the full combination. Okay. Now, in the first year, where this, if you talk from Vic Gupta, who talked about the effective field theory and the seeing the BSM physics in the light of effective field theory. So of course, so there are two versions of EFT. One is the SMEFT, where the Higgs is a part of your doublet. So this is the symmetry is before the electronic symmetry breaking. But we have also Higgs effective field theory, where Higgs is not a part of the doublet; it is a singlet. So it is the case where you have already had the electronic symmetry breaking. So this SMEFT is a part of the HEFT, and generally so far we mostly focus this SMEFT part. But we showed that it's also important to probe this sector where you have heft which are not SMEFT, and he showed that there are in recent years there are many interesting works in the theory side who show that this region is interesting for model building. Okay, and so he took a list of processes and to probe, and in these cases, if you consider all these processes, you need 17 dimension 6 operators in SMEFT. So you need only 17 measurements. So if you measure some weight and some kinematic distributions, those are sufficient to constrain those operators. But if you consider for heft, then you need a lot more measurements. So then if you go for differential measurements with multivariate analysis and so on. So that's more challenging. So in experiment, we are already doing it already. So we use the matrix element based method to probe different Higgs anomalous coupling. We use different final states, Higgs tau tau for electron, to constrain the Higgs to vector boson anomalous coupling, and also Higgs to gluon anomalous coupling, and also the equa coupling of Higgs to top quark. So we exclude the POCP odd hypothesis for Higgs to gluon coupling at 2.4 sigma, and topics pure topic CP coupling at 3.7 sigma. Okay, so the last one. So I also talked about the top Higgs coupling. So we use the TTZ final state or TZQ final state to prove the top Higgs coupling or the top or TZ coupling. This is similar to G-2 for top quark basically. And here you show the constraints in this 2D plane of electroweak dipoles basically, and we have also 1D constraints for different top quark couplings. That's basically my summary. So yeah, so I did not cover 3 talks in this summary because the slides were not there on Indigo. So we had 2 mini review talks by Kajori and Vic, both from TFR, and 9 parallel talks, and also large number of posters. So I stop and thank those who are still present here and not have left.
Okay, thanks, Dr. Suman. So I think we can go next to the neutrino physics working group. So Professor Siddharth Athar. So okay, so we have to hurry up. I will try. So I will just stand actually in 10.
I am told that there can be a power cut, therefore I have to summarize it in a very short time. See, there were 3 plenary talks in this neutrino physics session, one by Rahul Srivastav, who presented the theoretical status of neutrino physics, then Bipul Bhuiya on the experimental status on neutrino physics, and Indumati on India-based underground experimental status. Then there were 2 mini review talks, one by Poonam Mehta on physics with dune near and far detectors, and by Animesh Chatterjee on current status and future of sterile neutrino searches. 94 papers were submitted, 26 papers were selected for the oral presentation, and 68 papers were selected for the poster presentation. The papers mainly focused on searches for sterile neutrinos, non-standard interaction of neutrinos, neutrino oscillation parameters, neutrino mass modeling, Earth tomography, Lorentz invariance violation, neutrino cross-section studies, etc. As we know that there are various sources of neutrinos, both astrophysical, geo-cosmological, man-made and all that, and there were papers from almost covering many of these sources, and the important point is that these neutrino sources, the neutrino energies are not unique, and as you can see, it covers from a micro electron volt to more than 0 electron volt. By the end of this decade or the beginning of the next decade, upcoming experiments like DUNE, Hyper-K, Juno, NOVA, IceCube may provide answers to unknowns such as neutrino mass ordering, determination of mixing angle, whether it is less than or more than 45 degrees, determining CP violation in lepton sector, then also about the neutrino-less double beta decay, the neutrinos are Dirac neutrinos or Majorana neutrinos. Then perhaps we would be also possible to get answer about the origin of neutrino mass, neutrino mixing, why they are different from quark mixing. Is the 3-flavor neutrino picture complete? That means for these we need physics beyond the standard model. We have information about the neutrino oscillation parameters from the various neutrino sources like solar, reactor, atmospheric, beta decay and cosmology. And these are the present neutrino experiments which are going on. They are both they are reactors, atmospheric, accelerator and all that, and many experiments are coming up like Juno, IceCube, Hyper-Kamiokande and DUNE. There was a talk on INO. As we know, this is a very promising and indigenous experiment, and this is a mega science project jointly funded by DST and DAE, and there it is going to address many physics goals. Presently, mini ICL is running at Madurai, and around 40 PhDs have been produced in these, and we should, as a physics community, should come forward to make it a reality. Then there were many parallel sessions, and the talks were on neutrino non-standard interactions, a solution to NOVA and T2K tension, and it has been proposed that the future data from T2K and NOVA and experiments like T2K, Hyper-K and DUNE is expected to confirm the presence of non-standard interaction and also will help resolving the ambiguity that we have between T2K and NOVA. Then latest results from NOVA was discussed, which are found that the theta-13 is found to be consistent with what has been obtained by reactor experiments. No preference for CP conservation or violation has been obtained in this experiment. Also, data shows no evidence for a sterile neutrinos. Then there was a paper in parallel session on deuterated liquid scintillator, where it has been proposed that in Kudankulam nuclear power plant, one can place heavy water, and there it is possible to study charge current and as well as neutral current neutrino interactions, and especially new physics scenarios with sterile neutrinos. Then there was a talk on renormalization group evolution of neutrino angles and masses, why neutrino mixing angles are different from quark mixing angles, and whether they are same at Gutt scale, or whether there is a preference that the neutrinos are Majorana neutrinos rather being Dirac neutrinos. Then there was a paper on octet sensitivity restored in presence of a light sterile neutrino due to resonant matter effect. Then a paper was on a study of neutrinoless double beta decay and lepton flavor violation in a standard model extension with assuming the presence of sterile neutrinos. Then a cubic kilometer neutrino telescope which is going to come in the Mediterranean Sea. A paper was on neutrinos originating from WIMP annihilation in the sun. The upper limit of neutrino induced muon event rates have been estimated, and comparison has been made on the two different dark matter models, namely inert double model and minimal supersymmetric models. Then a study has been done to show that neutrino electromagnetic properties can be used to distinguish between Dirac and Majorana neutrinos by introducing neutrino magnetic moment in left-right symmetric model. There is a tension between microboon and mini-boon, and microboon first searches for low energy excess for no evidence of excessive events as seen by mini-boon, but they have not ruled out sterile neutrino hypothesis. There is another experiment, Dune, that is coming up, and it uses liquid argon time projection chamber, expected to come alive by 2029, will provide answer to questions like did neutrinos cause matter-antimatter asymmetry, determination of neutrino mass hierarchy, and many other problems. Then in all these neutrino experiments, the oscillation events are convolution of neutrino nucleon cross section convoluted over neutrino flux, target number of target particles, and time of interaction. And neutrino interactions are important to understand determination of backgrounds, reduction of systematic errors, as well as in the quest for CP violation and mass hierarchy. And presently we need a precision of 1 to 5% in cross sections, while presently this uncertainty is 25 to 30%. Therefore, there were many papers which discussed on the experimental possibility of studying nuclear medium effects at NE and Minerva, and as well as theoretical efforts which have been made to understand neutrino nucleon as well as neutrino nucleus interaction cross sections. As one can see that if we go to, this is the center of mass energy on the x-axis and q square on the y-axis. If we go from the higher resonance energy, then we have the contribution from higher resonances, and then we have the deep inelastic scattering region. Presently we don't have much knowledge about this higher resonance region, especially in the axial vector sector. Then this understanding of nuclear medium effects is also important in all the interaction channels, especially the results were presented for the deep inelastic scattering, where the nuclear medium effects may be classified into shadowing, anti-shadowing, AMC, and Fermi motion region. And Minerva is a dedicated experiment for which the analysis is going on, and a paper was presented to understand anti-neutrino nucleus interaction cross section in the using medium energy neutrino beam. That is all from this session. Thank you very much.
Thanks, Professor Athar. So, any quick comment? No? Thanks again. So, now I invite quark and lepton flavor sector working group. So Dr. Dinesh Kumar will be giving the summary. Working group.
Okay. So good afternoon to all of you. So first of all, I thank all the local organizing committee for giving me opportunity for convener of this working group, and I also thank to the other working group the working group convener of this Professor Rukmani Mohanta, Soumitra Nandi and Saurabh for giving me opportunity to present this report on this platform. So actually there were there were 14 talks and 2 mini review talk, 14 parallel talk, and about 30 posters in this working group at. I am going to present the summary of those, and sorry for if I have missed some important results. So first there was a mini review talk by Professor Jim Levy, and he talked about that what is the present status of this anomaly in RK star. So in the left side, this is the result for this RK 2021, and in the right side, this is the result for RK star from LHCb 2017, and this RK is having 3.1 sigma deviation from the standard model, and RK star is having 2.4 sigma deviation from the standard model. There was another result that was presented, that the analysis of B2K star LL in charge and neutral current modes, and it was found that similar efficiencies for E and mu sector, both E and mu sector, and also B2 Zepsi K, that was also studied in that was also presented in one of the work, and it was found that basically this B2 Zepsi K, these results are consistent with the world average. And the another result was B plus to K plus nu from Bell 2, and the sensitivity is just 63 femtobar inverse data is already close to the previous searches with significantly data set. Now moving to from this B2S sector to moving to the experimental results in TOS sector. So there was one mini review talk by Professor Swagato Banerjee. So he talked about the charged lepton flavor violating searches in tau sector. There is one he talked about the tau to L alpha, the analysis at Bell 2, and where this alpha is the spin 0 invisible boson. The 90%, 95% confidence upper limits from the Bell 2, these are shown in these plots. Basically these upper limits or these results shows that there are stringent constraints on the production of the invisible spin 0 boson from the tau decays. And the other results are for this tau lepton flavor violating processes. So there are limits from the different experiments, and the other projected limits from the Bell 2 are also in shown here. And the other result of this tau to 3 mu from the LHCb, that was also presented, and the branching ratio of tau to 3 mu on the upper limit at 90% confidence level, that is 4.6 into 10 to the power minus 8. Now coming to the other experimental results. So B sub s to pi 0 from Bell. So basically this B sub s to pi 0, this is the W exchange and penguin annihilation. This occurs because of the penguin exchange and this W exchange annihilation topological diagrams. And it was found that the upper limit on the branching fraction of at the 90% confidence level is obtained at 7.7 into 10 to the power minus 6. So this was given by, this is one of the talk by Jyotirmay Bora from IIT Guwahati. Thank you. So there was another talk by S. Kamble from IIT Madras. So he talked about the B sub S to ZEP psi from CMS, and what they did that they measured the CP violating phase phi s and the decay width difference delta lambda, which are measured using the 48,000 B sub S to ZEP psi candidates, and it was found that this phi s is minus 21 plus minus 44 milliradian, and it was found that these results are consistent with the standard model. In another talk by P. Sadangi, the B sub S to B sub S lifetime measurement from the CMS, and it was found that the B sub S to the lifetime of B sub S from B0 to ZEP psi Ks, this is consistent with the PDG value. And the first measurement of time dependent CP violation in B0 to K pi decay at Bell was presented by Sagar, and it was found that this branching ratio of B sub S to K0, this is also been consistent with the world average value. Now coming to the theory results. So there was one talk by Sirin from TIFR. So in this work what they did that they considered the G prime model, and this G prime model can have this complex coupling with the quarks. So with the complex coupling, so they did the global fit, and also they have taken this they found the parameter space for either taking the RK star or the ACP induced by BC to BS to ZEP psi, and they took this C9 is less than equal to 0 and C9 is equal to minus C10. One can see from here that by the inclusion of more data, that means in the case of global fit, the parameter space is shrinked, and from the this plots of the CP asymmetry, one can see that the CP asymmetry can be enhanced, means up to 15%, and also one can see that in the case of C9 is equal to minus C10, only the positive values of CP are allowed. But so basically the future measurement of this CP asymmetry will be that will give hint that that will be able to distinguish that about these two scenarios, this C9 is equal to minus C10 or C9 is less than 0. So the other theory result, from the other theory results, there was another talk by Nilakshi Das. So in that talk, they have studied the new physics effects in baryonic decays in lambda b to lambda mu mu or lambda b to lambda nu nu. So basically in this what they did that in the framework of SMEFT, they wrote the effective Hamiltonian with the standard model effective Hamiltonian, plus they have extended that new physics part, and they constrained the new physics Wilson coefficients with the help of the present B2S sector data, and with that parameter space they showed that what will be the change or what will be the new physics signatures in this lambda b to lambda or lambda star mu mu and the neutrino mode. Then another talk was by new physics effects in BC to tau c, eta c tau nu, and lambda b to lambda c tau nu, and b to d double star tau nu, and that talk was by Espriya. In this talk, they what they did that they wrote the most effective Hamiltonian in the B to C sector by adding the possible new physics different Lorentz possible Lorentz structures, and they studied the new physics effects in these decays. Then coming to the next one, there was another talk by Sabana Khan. So in this talk, she presented that how one can connect, by choosing the minimal coupling to explain the data in B2C sector, how can one make a connection between the B2 when we rotate. If you write the leptoquark coupling with the quarks in the mass eigenbasis, in weak eigenbasis, and then rotating in the mass eigenbasis, one can connect this B2C sector with the B2U sector. So in that case, definitely the couplings of the that particular U1 leptoquark model that can be constrained by B2C data, and those coupling can be directly, so using those coupling one can directly see the new physics effects of that particular model in the other B2U induced decays. So in this work, what she found that basically the differential branching ratio and the lepton flavor universality observable, this shows about 2 times enhancement in this particular case. And there was another talk by Anshika Bansal. So in this work, what they did that basically these differential amplitudes, these are the crucial theoretical, crucial non-perturbative input for the theoretical computation. So one has to do, from the exclusive B-meson analysis, B-meson decays, once one know that this inverse moment, these are the important parameters. So one need to, but in the case of D-meson, there is no systematic computation. So what one has to do that there should be, how to handle this in the case of D-meson, or how to compute the this inverse moment in the D-meson case. So in this work, she talked about how to compute the inverse meson in the and they get that this estimated value of the inverse moment turns out to be 0.35 GeV. So thank you.
Thanks, Dr. Dinesh. So I think we will go for top quark and electric physics by Dr. Sorik. So we have asked that power cut to be delayed, but in between if goes, we will continue. It will be like short for some maintenance. So.
Hello everyone. So I was not the convener of this particular working group, but I was roped in to give this summary. So moving ahead, it doesn't work. So here is a list of different top quark production process. So the dominant one is obviously the pair production, followed by the single top production, and then we have top plus friends, where we have vector bosons, additional vector bosons produced along with tops, as well as jets, and even one additional pair of top quarks, which is extremely interesting, which I will come to later. So this was also shown by Arun Nayak during his plenary talk. And let's come for TT bar cross section. So this is a good comparison of theory predictions with the experimental results. So all these theory predictions are accurate of the order of NNLO plus NNLL, and we see that at different center of mass energies the experimental results agree with theory very precisely.
and we do have a new measurement at 13.6 CV with only 1.2 femtobarn inverse data. The most precise measurement at 13 TV comes out to be 826.4 picobarn with a 2.4% of uncertainty, and the experimental uncertainty is currently lower than the theory uncertainties, which is of the order of 6%. So, following the pair production, we have the electroweak top production. There are three main production modes, T channel being the dominant, and here is the summary of the cross sections compared with theory, and all these theories are accurate up to NLO plus NNNL calculations. And CMS has the most precise measurement of the T channel cross section, and all these cross sections are proportional to the VTB square. So, this gives us a direct handle to estimate VTB by measuring these cross sections. Now, let us go to top plus friend. So, we have TT bar plus Z or gamma production, which was discussed in the working group, and from these measurement of these cross sections differentially, one can actually extract the anomalous couplings between the T gamma or the TZ vertex, and one can actually get limits, and the current measurements are agreeing with standard model within 1 sigma or 2 sigma level. This is a summary of different summary of the cross section measurements of different TT bar plus vector boson production. So, mostly they agree with the predictions within uncertainties. Now, going to production of 4 tops. So, this is extremely important because this is sensitive to the Higgs to top couplings, and this is a summary of Atlas and CMS results, and what CMS has recently performed a combination with full run to data, which has a observed significance of 3.9 sigma. So, we have evidence of 4 top final state reported very recently, and from this kind of cross section measurement, one can extract the limit on the top Yukawa coupling, and the current observed limit is of around 1.8 observed upper limit. Now, one can also measure the mass of the top quark, and one of the important process is single top, and Mintu presented measurement of the top quark mass in single top process, although it is not the most dominant process, but one can still measure the mass using multivariate techniques, and where here the top quark is reconstructed from its decay product, and in the reconstruction the W mass constraint is used, and a fit to this zeta variable is performed, and this result is compared with the previous results at from run 1, and also other results from run 2, and they agree within the uncertainties. And this is the first time in this particular rare production mode we have achieved a precision which is below a GeV. So, here is a summary of the top mass measurements. So, here there was a question during the plenary session regarding the average. So, this average belongs to a combination of the run 1 LHC and Tevatron results, and in run 2 CMS has changed the jet reconstruction by changing the cone size. Also the jet energy scale uncertainty determination have improved, and consequently all the CMS measurements are found to be slightly lower value compared to the previous average. And in the larger context, the top quark mass is extremely important in the electroweak symmetry breaking mechanism, because the Higgs self coupling depends, the correction on the Higgs self coupling depend on the 4th power of mass. Now, if you evolve this self coupling following RGE up to the Planck scale, depending on the mass, we can determine where exactly it reaches the floor at 0, and if it and based on that we can determine whether we are living in a stable, metastable or unstable electroweak vacuum. So, top quarks are also a rich source of W bosons, and one can actually calculate the rate of ratio of the branching ratios between W to tau nu and W to mu nu. Atlas has performed such a measurement, and this measurement is in tension with the previous LEP result. So, the technique that is used by Atlas is to measure the impact parameter, where the top, that is decaying to decaying to tau, is further decays to a mu and gives a larger impact parameter, whereas the top that decays directly to a muon in the final set gives a lower impact parameter. These kind of discriminants are used to extract the ratio. This is the most precise measurement so far, and it agrees with the standard model. Similar measurements were performed by CMS by measuring the branching ratios of different W leptonic decays, and but in diboson and W plus jets event, and all the results agree with the standard model prediction, and they have some tension with the previous LEP results, as you can see from these contour plots. This is a summary of the CMS measurements at different center of mass energies of the diboson production. So, mostly the results agree with the calculations. So, we have not found any significant deviation so far. And this was a nice result that was presented by Ankita, the diboson production in double pattern scattering, and the effective cross section was found to be 12.2 millibarn, and which is 6.2 standard deviations. This is the first observation with a significance of 6.2 standard deviation. So, now I come to my summary. So, in this particular topic, there was one plenary, joint plenary with Higgs given by Arun Nayak. There was one parallel session. The parallel session had 2 mini reviews and 2 parallel talks. There were several interesting posters based on different couplings, and we had some lively discussions during the parallel session and also during the poster session. I would like to thank all the local and national organizers and the volunteers for making this conference into a big success. Thank you.
Thanks, Saurabh. So, a quick moment. So, yeah, so I think it's better we have a tea break now, because if light goes in between, okay. So, we will come back and wait for the next DAE still. So, come.